The Roman Empire's expansion across Europe, North Africa, and the Middle East created sprawling urban centers that demanded a reliable supply of fresh water. This need was met through an extensive network of aqueducts, engineered channels designed to deliver spring and river water to cities, military camps, and industrial sites. These structures were not simply conduits, they represented a sophisticated understanding of hydraulics, exploiting precise gradients to maintain a steady flow over considerable distances. At valleys or depressions, inverted siphons conveyed water under pressure, while settling basins regulated delivery to public baths, fountains, and private homes. The scale of this infrastructure was remarkable. Aqueducts carried water on arches, through tunnels or buried pipelines, often spanning many kilometers. Beyond providing drinking water, Romans harnessed the power of flowing water using watermills, devices employing overshot and undershot wheels to drive grain mills and other industries. The consistent operation of these aqueducts and mills was paramount. Regular maintenance ensured both water quality and flow rates. This infrastructure underpinned urban growth, public hygiene, and socio-political cohesion within the Roman Empire, leaving a legacy that continues to inform modern engineering practices. The consistent operation of these aqueducts and mills was paramount. Regular maintenance ensured both water quality and flow rates. This infrastructure underpinned urban growth, public hygiene, and socio-political cohesion within the Roman Empire, leaving a legacy that continues to inform modern engineering practices. Maintaining this vast network required a dedicated workforce whose efforts are only now beginning to be fully understood through recent archaeological investigations. Analyses of mineral deposits, specifically carbonate crusts, within aqueducts reveal evidence of repeated manual removal of calcite at intervals ranging from 1 to 5 years. This upkeep aligns with historical advice on seasonal maintenance and likely reflected fluctuating economic conditions impacting the availability of labor. Similarly, studies examining pipelines supplying public fountains in Pompeii have utilized elevation surveys and hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second, demonstrating how factors like pipe diameter and surface roughness influenced water distribution. These investigations highlight that the functionality of Roman aqueducts was not simply a matter of initial construction, but depended on ongoing human intervention. These investigations highlight that the functionality of Roman aqueducts was not simply a matter of initial construction, but depended on ongoing human intervention. Analyses of incrustations in a southern French aqueduct show repeated manual removal of calcite at intervals of 1 to 5 years, matching textual advice on seasonal upkeep and reflecting shifting socioeconomic conditions. This suggests a cyclical pattern of maintenance influenced by factors beyond purely technical considerations. Similarly, studies examining pipelines supplying public fountains in Pompeii have utilized elevation surveys and hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second, demonstrating how factors like pipe diameter and surface roughness influenced water distribution. The Roman Empire's water management systems represent a significant achievement of pre-industrial engineering. Central to these networks were aqueducts, structures designed to deliver spring and river water to urban centers, military camps, and industrial sites. These channels conveyed water over considerable distances, exploiting precise gradients to maintain a steady flow driven by gravity. At critical crossings, inverted siphons, closed conduits that leveraged hydraulic head, allowed water to pass beneath the terrain. Early Roman aqueducts were initially straightforward constructions, but their development reflects an evolving understanding of hydraulics and engineering principles. The scale and complexity grew alongside urbanization. As cities expanded, so too did the need for reliable water sources beyond what could be readily accessed within city limits. Studies utilizing geomatic measurement techniques have been applied to surviving aqueduct sections south of Rome, using high-precision leveling to reconstruct original gradients and assess centuries of subsidence. These surveys enabled more accurate flow reconstructions. The Barbagal watermill complex, constructed in the 2nd century CE, exemplifies advanced hydraulic planning. Carbonate encrustations were used to model a series of 16 overshot wheels within a bespoke flume design, Europe's first industrial-scale milling installation. Analyses of these incrustations in a southern French aqueduct show repeated manual removal of calcite at intervals ranging from 1 to 5 years. This practice likely reflected fluctuating socio-economic circumstances impacting labor availability. Stable isotope records extracted from carbonate layers in an aqueduct channel located in southwestern Turkey have provided chronologies linked to the reign of Nero, demonstrating how these deposits can preserve data about both past climate patterns and infrastructure events. Reconstruction of the Barbagal watermill complex further leveraged carbonate incrustations to model a series of 16 overshot wheels, highlighting advanced hydraulic planning in late Republican and early imperial engineering. Studies combining elevation surveys with hydraulic modeling have estimated flow rates between 0.1 and 2.5 liters per second within pipelines supplying public fountains in Pompeii, illuminating how pipe diameter and surface roughness control distribution under gravity. The Roman aqueduct's ability to deliver water over considerable distances relied on more than just gravity. It depended on maintaining a remarkably consistent gradient, often imperceptible to the naked eye. This precision was achieved through sophisticated surveying techniques and tools. Among these were instruments like the groma, a device used for establishing straight lines and right angles. It consisted of a vertical staff with horizontal arms at its top, each fitted with plumb bobs to ensure accuracy. Surveyors employed the groma to lay out the initial course of an aqueduct channel, ensuring that it followed a precise alignment. Another key tool was the dioptra, essentially an early form of theodolite. While descriptions of its exact construction vary, it allowed surveyors to measure horizontal and vertical angles with considerable accuracy. This was crucial for determining the slight downward slope necessary for gravity-driven flow. The hydraulic gradient, the slope of the water's head that propelled the flow, had to be carefully calculated and maintained along the entire length of the aqueduct. To assess this, Roman engineers also used a courbates, a sighting rail supported by adjustable feet. This allowed surveyors to establish a level line across uneven terrain, further refining the gradient calculations. These instruments, combined with skilled labor, enabled the Romans to achieve an accuracy that facilitated the construction of these impressive water systems. The precision afforded by these instruments extended to the construction of inverted siphons, crucial for maintaining a consistent gradient when aqueducts crossed valleys. As noted in studies examining Roman water transport, these siphons utilized stone, ceramic, and lead, requiring careful solutions for sealing joints and releasing trapped air, challenges addressed through established practices documented in Vitruvian treatises. Modern geomatic surveys, employing high-precision leveling techniques on surviving sections south of Rome, have further refined our understanding of original gradients. These measurements allow researchers to reconstruct the aqueduct's intended slopes and assess the impact of centuries of subsidence on their alignment. Such analyses contribute to more accurate flow reconstructions and offer avenues for investigating long-term geodynamic shifts affecting these structures. The application of these techniques demonstrates a continued effort to understand and quantify the remarkable engineering feats achieved by the Romans. These instruments facilitated not only accurate gradient establishment, but also precise alignment of aqueduct segments, crucial for maintaining consistent flow and minimizing erosion. The dioptra, a sighting instrument akin to a modern theodolite, enabled surveyors to measure horizontal and vertical angles with considerable accuracy. This was vital for laying out straight stretches of aqueducts across varied terrain and ensuring that curves adhered to calculated radii. Furthermore, the groma allowed for the precise bisection of angles, essential in constructing right-angled corners for settling tanks and distribution structures along the channel. The combination of these tools, the chorobates for level lines, the dioptra for angular measurements, and the groma for accurate corner establishment, represented a sophisticated system that underpinned Roman hydraulic engineering. The Roman aqueducts' longevity is owed to more than just ingenious surveying and gradient management. Their enduring nature also stems from a remarkable construction material, opus caementicium. This hydraulic concrete, as it's often called, allowed the Romans to build structures capable of withstanding constant water pressure and environmental stress for centuries. While the precise recipe varied depending on local resources and intended application, core components remained consistent across the empire. The fundamental ingredient was pozzolana, a volcanic ash found in regions like Pozzuoli near Naples. When mixed with lime and aggregate, typically small stones or rubble, pozzolanic materials created a cementitious compound that possessed unique properties. Unlike traditional mortar composed solely of lime, opus caementicium underwent a chemical reaction when exposed to water, forming calcium silicate hydrate, the binding agent responsible for its strength. This process continued over time, effectively causing the concrete to strengthen and become more durable with exposure to moisture, a phenomenon largely unknown to builders before the Romans. The aggregate used also played a crucial role. Careful selection of stones ensured minimal porosity within the mixture, further enhancing water resistance. The aggregate used also played a crucial role. Careful selection of stones ensured minimal porosity within the mixture, further enhancing water resistance. The precise composition varied regionally, reflecting the availability of local materials. For example, in areas lacking abundant pozzolana, builders might incorporate crushed brick or tile as a substitute, though with potentially reduced durability. Vitruvius, in his De Architectura, acknowledged this variability, noting that the quality of the aggregate significantly impacted the final product's strength and longevity. He advised careful inspection of materials before use, emphasizing the importance of selecting stones free from impurities that could compromise the concrete's integrity. Furthermore, the ratio of lime to pozzolanic material was also subject to adjustment. A higher proportion of pozzolana generally resulted in greater impermeability, but might also increase setting time and require more careful mixing techniques. Recent investigations into Roman aqueducts have revealed evidence of experimentation with different aggregate types and binder ratios, suggesting an ongoing process of refinement aimed at optimizing performance based on local conditions and specific structural demands. The variability extended to the curing process itself. Roman builders understood that proper hydration was essential for achieving optimal strength, and techniques varied depending on climate and available resources. In drier regions, concrete might be covered with damp cloths or straw to prevent rapid water loss during initial setting. Conversely, in wetter climates, measures were taken to ensure adequate ventilation and avoid excessive moisture absorption. Studies of pipelines supplying Pompeii's public fountains have combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second, illuminating how pipe diameter and surface roughness controlled distribution under gravity. The durability of Roman aqueducts resulted from innovations in construction materials, specifically the concrete used to bind everything together. While aggregate stones or rubble formed the bulk of the mixture, a unique combination held it all in place, proving remarkably resistant to weathering and erosion over centuries. This binding agent relied heavily on pozzolana. Pozzolana is a volcanic ash found near places like Puteoli, from which its name derives. The Romans recognized this material's properties. When mixed with lime and water, it created a cement-like substance stronger and more durable than traditional lime mortar alone. This reaction produced what we now call Roman concrete. Sourcing varied depending on location, sometimes quarried directly from volcanic deposits, other times collected from riverbeds, but its consistent inclusion in aqueduct construction suggests a deliberate understanding of its benefits. The quality of pozzolana varied considerably based on geological origin. Some deposits contained impurities that affected the strength and durability of the resulting concrete. Roman builders likely developed methods for assessing material quality, perhaps through trial mixing or observation of setting times. Its inclusion within the core fill could vary based on economic factors and structural requirements. Pozzolana was not always consistent across all components of an aqueduct. It frequently appeared in mortar binding facing stones. The logistical complexities extended to the labor force involved in pozzolana extraction and transport, which likely included corvée labor alongside enslaved individuals or wage laborers. The uneven distribution of deposits influenced settlement patterns and trade networks, creating localized economies centered around resource extraction and processing. While Puteoli remained a primary source, its distance from many project sites necessitated alternative supply chains. Evidence suggests that Romans sought out similar volcanic materials in regions like Tuscany and Crete, transporting the ash often in bulk using ships or carts, which added to overall construction costs. The Roman Empire's water management networks were extensive and sophisticated, relying heavily on aqueducts to deliver spring and river water to urban centers, military camps, and industrial sites. These channels conveyed water over considerable distances, exploiting precise gradients to maintain a steady flow driven by gravity. To overcome challenging terrain, Roman engineers developed innovative solutions beyond simple open channels. One key innovation was the use of arcades. Aqueducts frequently traversed valleys or uneven ground using arches, elevating the channel and maintaining the necessary gradient. Where depressions proved too deep for a continuous arcade, inverted siphons offered another solution. These were closed-pressure conduits designed to convey water under pressure across these low points. The construction of inverted siphons presented unique engineering challenges, requiring careful attention to sealing, jointing, and air release mechanisms. Materials used included stone, ceramic, and lead, reflecting available resources and engineering suitability for each application. Established best practices informed construction methods, as documented in writings like those of Vitruvius. The design of inverted siphons presented particular challenges related to maintaining a seal against air and water loss across the conduit's length. Solutions involved careful jointing techniques and mechanisms for releasing trapped air, which could otherwise disrupt flow or damage the structure. Studies of pipelines supplying public fountains in Pompeii combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second. Pipe diameter and surface roughness influenced distribution under gravity. These factors demonstrate a nuanced understanding of fluid dynamics within the Roman system. Geomatic measurement techniques have been applied to surviving aqueduct sections south of Rome, using high-precision leveling to reconstruct original gradients and assess centuries of subsidence. This work enabled more accurate flow reconstructions and paved the way for future geodynamic studies of aqueduct deformation over millennia. Analyses of carbonate crusts in a southern French aqueduct revealed repeated manual removal of calcite at intervals of 1 to 5 years, mirroring textual advice on seasonal upkeep. The Roman aqueduct system stands as a testament to their engineering prowess, an enduring symbol of civilization and innovation. While Rome's achievements extended to military conquest, civic architecture, roads, emperors, and sculpture, these were all reliant on a vital resource: water. The Aqua Appia, completed in 312 BCE, marked the beginning of this sophisticated network. It was sponsored by censor Appius Claudius Caecus, who also oversaw construction of the Appian Way. The Aqua Appia differed from later aqueducts. It ran almost entirely underground. Roman engineers did not invent water management techniques. Earlier Mediterranean peoples, such as the Minoans on Crete, had developed rain harvesting and filtering systems. However, no previous system matched the sophistication and reach of the Roman aqueduct. Construction began with a design phase, followed by digging shafts at intervals of around 230 feet, using an ancient Persian technique known as quanat. These shafts facilitated the removal of dirt and lowered building materials for channel construction. Stone blocks were lowered via cranes to line tunnel walls. Bricks or concrete were sometimes used depending on local availability. A waterproof layer of opus signum, a mortar made from crushed tiles and amphorae, sealed the channels. The route was carefully planned to follow the land's natural grade whenever possible, often requiring long detours. The shafts facilitated the removal of dirt and lowered building materials for channel construction. Stone blocks were lowered via cranes to line tunnel walls. Bricks or concrete were sometimes used depending on local availability. A waterproof layer of opus siginum, a mortar made from crushed tiles and amphorae, sealed the channels. The route was carefully planned to follow the land's natural grade whenever possible, often requiring long detours. Construction of the Aqua Appia presented challenges beyond simple engineering. Accounts indicate difficulties arose during its execution. One funerary monument found at Béjaïa in Algeria details setbacks encountered by engineer Nonius Datus, who oversaw construction around AD 152. The text describes lobbying for improved water supply and recounts instances where excavation teams did not meet as planned, necessitating adjustments to the route. Furthermore, bandits attacked the site, forcing Datus to flee. These accounts suggest that even with careful planning, unforeseen circumstances could significantly impact project timelines and require adaptation. Specialized workers known as equerri were responsible for maintaining the aqueduct's proper operation and cleanliness. They carried out repairs and systematically cleaned channels to prevent blockages. The channel along which water flowed was kept covered, and tanks called pistonae limeriae were placed along the route to decant impurities. The Aqua Claudia stands as a testament to Roman engineering ambition. Completed between 38 and 52 CE, it was one of several aqueducts built to meet Rome's escalating water demands. Ancient masters created a vast network of pipes, channels, and bridges to bring water to the city, creating an enduring symbol of Roman civilization and innovation. The need for increased supply arose as Rome's population grew. By the 1st century AD, it was thought to have reached 1 million people. Caligula initiated construction, but his successor Claudius finished the work and named it Aqua Claudia. Like other aqueducts, its design drew upon earlier Mediterranean traditions of water management. The Minoans on Crete developed sophisticated rain harvesting systems as early as 3000 BC, and these techniques were later adopted across the Greek world. However, no previous system matched the scale and reach of Roman aqueducts. These structures stretched from Spain to Syria, carrying not only water but also proclaiming Rome's power. The Aqua Claudia's route extended for 37 miles, though the distance as the crow flies between its source and Rome was about 31 miles. Engineers followed the land's natural grade whenever possible, creating channels that ran underground or at ground level. When valleys presented an obstacle, they constructed impressive arched structures, a popular image associated with aqueducts. The construction process itself required considerable resources and manpower. A series of shafts were dug at intervals following an ancient Persian technique known as qanat. These shafts facilitated the removal of dirt and delivery of building materials. Stone blocks were lowered using cranes to line the tunnel walls, sometimes utilizing bricks or concrete, depending on local availability. Waterproofing was achieved with opus signinum, a mortar made from crushed tiles and amphorae fragments. The construction process itself required considerable resources and manpower. A series of shafts were dug at intervals, following an ancient Persian technique known as kanat. These shafts facilitated the removal of dirt and delivery of building materials. Stone blocks were lowered using cranes to line the tunnel walls, sometimes utilizing bricks or concrete, depending on local availability. Waterproofing was achieved with opus signinum, a mortar made from crushed tiles and amphorae fragments. One Roman funerary monument found at Béjaïa in Algeria recounts difficulties encountered during construction. Teams excavating tunnels did not meet as planned, and the site experienced bandit attacks. A technician named Nonius Datus escaped such an attack bruised and naked. Specialized workers known as aqueducts were responsible for maintaining the aqueduct's proper operation and cleanliness, carrying out repairs and systematically cleaning channels to prevent blockages. They ensured that tanks called piscinae limeriae were used to decant impurities from the water. The Aqua Aurelia, a vital artery of Roman water supply, relied on an impressive feat of engineering, the Pont du Gard. This structure, located in southern France, isn't merely a picturesque bridge. It's a critical component of the aqueduct system itself. Ancient masters created a vast network of pipes, channels, and bridges to bring water to Rome, creating an enduring symbol of Roman civilization and innovation. The Pont du Gard stands as a testament to Roman ingenuity, built to carry water from its source near the town of Uzès over the Garden River Valley. The structure's design reflects a sophisticated understanding of both hydraulics and architecture. Roman engineers would create a gentle downward slope all the way from start to finish, since the only force powering the water's progress was gravity. Only valleys or gullies necessitated a monumental arched structure. For most of its route, water ran along underground or ground-level channels. The arches themselves are not simply decorative. They served a crucial purpose in maintaining that consistent downward slope while traversing uneven terrain. Construction involved immense labor and careful planning. Basic Roman construction materials were stone blocks, concrete, mortar, tiles, and bricks. A series of shafts, putti, were dug at intervals to facilitate the process. Workmen lowered stone blocks, using cranes to form the lining for the tunnel walls. Depending on local availability, bricks or concrete were sometimes used for this purpose. The channel was usually waterproofed with a layer of opus signinum, a kind of mortar made of fragments of crushed tiles and amphorae. As the construction advanced, wooden scaffolding aided the workmen. A wooden structure, known as centering, bore the arch's weight until the last stone was laid. When removed, the slotted stones could support their own weight. The Pont du Gard features multiple tiers of arches, a testament to the Romans' ability to distribute weight and create stable structures. The monument at Béjaïa provides a rare glimpse into the challenges faced during construction, detailing setbacks such as discrepancies in tunnel meeting points and attacks by bandits. These difficulties highlight that even with meticulous planning, unforeseen obstacles arose. The text recounts how Nonius Datus narrowly escaped an attack, emphasizing the risks inherent in such large-scale projects. Specialized workers, known as aqueducts, were responsible for maintaining the aqueduct's operational status and cleanliness. Their duties included repairs and regular channel cleaning to prevent blockages and ensure water quality. These channels remained covered to minimize contamination, with Pistinae limaria, sedimentation tanks, placed along the route to remove impurities. The Segovia Aqueduct in Roman Spain stands as a testament to their enduring legacy. Traditionally attributed to Augustus, recent studies suggest it dates from the reign of Trajan in the 2nd century AD. Known locally as El Puente, its 168 arches remain remarkably well preserved, having been consistently utilized for nearly 2 millennia. The construction of Roman aqueducts demanded a vast workforce, encompassing slaves, free laborers, and skilled engineers. While precise numbers remain elusive, it's clear that building even a single aqueduct represented a monumental undertaking requiring significant human investment. The labor itself was physically grueling, often involving extended periods spent digging tunnels or quarrying stone under harsh conditions. Much of an aqueduct's course lay underground along channels that required huge resources and manpower to build. Once the route had been designed, a series of shafts were dug at intervals following an ancient Persian technique known as qanat. When the planned depth was reached, construction of the channel began. The shafts were used to carry away dirt in baskets and send down building materials. A crane was used to lower stone blocks, which may have been brought from a nearby quarry, to form the lining for the tunnel walls. Depending on the local availability of materials, bricks or concrete were sometimes used for this purpose. The channel was usually waterproofed with a layer of opus signum, a kind of mortar made of fragments of crushed tiles and amphorae. Roman engineers followed the land's natural grade wherever possible, building channels underground, even if that meant having to make long detours. Evidence suggests that slaves formed a significant portion of this labor force, alongside free workers who were likely paid wages or compensated with food rations. The monument found at the city of Béjaïa in Algeria commemorates one such engineer, Nonius Datus, and recounts difficulties encountered during construction. This text describes how teams excavating tunnels sometimes failed to meet where planned, and that bandits attacked the site, forcing Datus to flee for his life. These accounts underscore the inherent risks faced by those involved in aqueduct construction. A large group of specialized workers known as a quarry ensured the aqueduct's proper operation and cleanliness. These technicians carried out repairs and systematically cleaned the channels to prevent blockages and maintain a decent water quality. The monument at Béjaïa also describes the tools used by Datus's workers, including iron drills and picks to excavate the rock and wooden wedges for splitting stone. The text indicates that these tools were regularly damaged and needed replacement, adding further expense to the project. Accounts such as this suggest that construction was not a continuous process. Interruptions due to weather, tool failure, or labor disputes likely occurred. While a quarry maintained existing channels, repairs to tunnels often required reopening sections of the structure, a laborious undertaking in itself. The monument notes that Datus's team had to rebuild portions of tunnel already completed when unexpected geological conditions arose. This necessitated re-excavation and relining, further delaying progress and increasing costs. The construction of Roman aqueducts required ongoing attention beyond their initial building. The infrastructure's longevity depended on regular maintenance, a process as vital to the system's success as the original engineering. This upkeep ensured consistent water quality and flow rates, underpinning urban growth and public hygiene. Evidence from southern France reveals that calcite deposits within aqueduct channels were manually removed at intervals of 1 to 5 years. This practice reflected both seasonal routines and shifting economic conditions. The work itself involved a variety of tasks, Cleaning channels was essential to prevent sediment buildup, which would impede water flow, while inspection identified cracks or weaknesses in the structure. Repairs addressed damage from natural events or general wear. These could range from patching small leaks to rebuilding sections of tunnel when unexpected geological conditions arose. The removal of calcite deposits was a recurring need, demonstrating an understanding of how mineral buildup impacted performance. Studies examining pipelines supplying Pompeii's public fountains suggest water flowed at rates between 0.1 and 2.5 liters per second, highlighting the importance of maintaining consistent flow through careful upkeep. The varied nature of maintenance work likely resulted in a range of laborers employed by aqueduct administrators. Evidence suggests both specialized craftspeople and seasonal workers participated in upkeep efforts. Removing calcite deposits required individuals skilled in manual labor and potentially possessing tools adapted to scraping or chiseling mineral buildup from channel walls. Similarly, repairing structural damage necessitated masons familiar with Roman concrete techniques, capable of rebuilding sections of aqueduct where necessary. Workers also needed to understand hydraulic principles to ensure consistent flow rates through adjustments to pipe diameter and surface roughness. The scale of these operations suggests a hierarchical system, with overseers directing teams of laborers and reporting on progress to aqueduct officials. The intervals for calcite removal, 1 to 5 years, likely depended upon local conditions and the availability of labor, reflecting shifting socio-economic factors impacting maintenance schedules. Specialized foremen were responsible for coordinating repairs to specific aqueduct segments, particularly those traversing difficult terrain or experiencing frequent structural issues. These individuals possessed a working knowledge of hydraulic principles and could adjust pipe dimensions to optimize flow rates, valuable in diagnosing and rectifying localized blockages or leaks throughout the entire system. Accounts indicate that some laborers specialized in constructing temporary diversions during major repairs, allowing water delivery to continue while work progressed on damaged sections. The precise organization of these teams remains unclear, but it is probable that local communities contributed labor alongside those directly employed by Roman authorities, particularly for routine maintenance tasks like calcite removal. The long-term functionality of Roman aqueducts depended on more than just initial construction. Regular maintenance was essential to preserving water quality and flow rates. While specialized foremen oversaw repairs to specific segments, a broader system of oversight ensured continued operation across the entire network. Accounts indicate that inspections played a crucial role in this process. Analyses of carbonate crusts within aqueducts reveal repeated manual removal of calcite at intervals of 1 to 5 years. This practice reflected advice on seasonal upkeep and addressed shifting socio-economic conditions impacting maintenance schedules. The precise nature of these inspections remains somewhat unclear, but the need for them is evident from the deposits left behind. Beyond simply identifying blockages or leaks, inspectors likely assessed structural integrity, monitoring for subsidence or damage to channels and inverted siphons. The construction of these pressure conduits, made from stone, ceramic, and lead, presented unique sealing, jointing, and air release challenges that would have required careful observation and occasional adjustment. Geomatic measurement techniques applied to surviving aqueduct sections, south of Rome, demonstrate how high-precision leveling was used to reconstruct original gradients and assess centuries of subsidence, suggesting a level of scrutiny extended even long after initial construction. This ongoing assessment allowed for adjustments to be made, ensuring the consistent delivery of water to urban centers, military camps, and industrial sites. These geomatic surveys also facilitated the identification of areas where subsidence had altered the aqueduct's gradient, potentially impacting flow efficiency and requiring remedial action. The Roman water transport publication details how inverted siphons, constructed from stone, ceramic, and lead, presented unique challenges in sealing, jointing, and air release. Careful observation and adjustment would have been necessary to maintain their functionality. Vitruvian treatises provided context for best practices in pressure line construction, suggesting a formalized understanding of these issues within the engineering community. While specific names of individual inspectors or engineers are rarely recorded directly in surviving documentation, the scale and complexity of aqueduct maintenance imply a hierarchical system with varying levels of expertise. The repeated removal of calcite deposits indicates that inspection schedules were likely influenced by seasonal patterns and broader economic conditions, suggesting some degree of flexibility within the oversight process. The hierarchical system likely included specialized surveyors who used geomatic techniques to monitor gradient changes and identify areas requiring intervention, alongside engineers responsible for designing repairs or modifications to aqueduct structures. The Roman water transport publication highlights that sealing, jointing, and air release challenges in inverted siphons demanded expertise beyond basic construction. This suggests a tiered system where experienced craftspeople oversaw less skilled laborers. Analysis of carbonate crusts within aqueducts reveal repeated manual removal of calcite deposits at intervals influenced by seasonal patterns and broader economic conditions, implying some degree of flexibility within the oversight process. The Roman Empire's water management networks were among the most extensive and sophisticated of the pre-industrial world, with aqueducts serving as a central component. These engineered channels delivered spring and river water to urban centers, military camps, and industrial sites, exploiting precise gradients to maintain a steady flow over considerable distances. At points where valleys intervened, inverted siphons conveyed water under pressure. The scale and consistency of this infrastructure underpinned urban growth, public hygiene, and socio-political cohesion. Beyond simply providing drinking water, aqueducts fueled other aspects of Roman life. Settling basins and distribution castellums regulated the delivery of water to public baths, fountains, and private homes. Furthermore, Romans harnessed hydraulic power through water mills, utilizing overshot and undershot wheels to drive grain mills and workshops. Regular maintenance was vital. Cleaning, inspection, and repair preserved both water quality and flow rates. Recent investigations into carbonate crusts within Roman aqueducts have revealed insights into environmental history and maintenance regimes. Analyses of incrustations in a southern French aqueduct show repeated manual removal of calcite at intervals of 1 to 5 years, mirroring textual advice on seasonal upkeep and reflecting shifting socio-economic conditions. The distribution of water also reflected social hierarchies within Roman cities. While public fountains provided access for all, the availability of piped water directly to private homes was a privilege afforded primarily to wealthier citizens. Studies of pipelines supplying Pompeii's public fountains indicate flow rates between 0.1 and 2.5 liters per second, demonstrating how pipe diameter and surface roughness influenced distribution under gravity. The construction of elaborate bath complexes, often featuring heated pools and sophisticated hygiene facilities, further underscored the disparity in access to clean water based on social standing. Roman engineers also addressed challenges associated with conveying water across valleys through the use of inverted siphons constructed from stone, ceramic, or lead. Vitruvian treatises contextualize these ancient construction best practices. Geomatic measurements applied to aqueduct sections south of Rome have revealed subsidence over centuries, impacting original gradients and influencing flow reconstructions. The use of lead for some pressure conduits, as detailed in reviews of Roman water transport, presented ongoing challenges related to corrosion and potential contamination, though methods existed to mitigate these risks. Geomatic surveys applied to surviving aqueduct sections south of Rome have revealed subsidence over centuries, impacting original gradients and influencing flow reconstructions. Such shifts necessitated adjustments to maintenance practices and occasionally required re-engineering of conduit alignments. The construction of Roman aqueducts necessitated significant interventions into the natural landscape and required substantial quantities of raw materials, resulting in localized environmental impacts. Quarrying for stone, pozzolana, a volcanic ash crucial for creating hydraulic concrete, and other building components altered terrain and disrupted habitats. The scale of these operations varied depending on the specific project. Some aqueducts drew upon readily available local resources, while others required expeditions to distant sources. The extraction of pozzolana, in particular, left a mark on volcanic regions like those around Vesuvius and other Campanian sites. Quarrying created pits and altered drainage patterns, potentially contributing to erosion and sedimentation in nearby waterways. Similarly, the sourcing of stone for arches, piers, and channel linings involved considerable excavation, often impacting forests used as timber supports during quarry operations. The transportation of these materials, stone blocks weighing several tons, pozzolana bagged or transported in bulk, further contributed to landscape disturbance through road construction and overland movement by animal-powered carts or human labor. While the extent of deforestation directly attributable solely to aqueduct construction remains difficult to quantify precisely, it undoubtedly occurred as a consequence of material extraction and transport activities. The sourcing of stone for construction also involved significant environmental disruption. Quarrying operations often targeted areas with suitable rock formations, leading to localized deforestation as timber was needed to support quarry walls and transport extracted blocks. While precise figures are unavailable, the demand for wood likely intensified pressure on forests already impacted by agricultural expansion and fuel needs. Furthermore, the creation of roads to facilitate material transport contributed to soil erosion and habitat fragmentation. The sheer volume of excavated earth generated substantial waste piles, which altered local topography and potentially contaminated water sources through sediment runoff. Although Roman engineers attempted mitigation strategies, such as terracing quarry faces or constructing retaining walls, the scale of construction frequently overwhelmed these efforts, leaving a lasting imprint on the landscape. The creation of roads to facilitate material transport contributed to soil erosion and habitat fragmentation. The sheer volume of excavated earth generated substantial waste piles, which altered local topography and potentially contaminated water sources through sediment runoff. Although Roman engineers attempted mitigation strategies, such as terracing quarry faces or constructing retaining walls, the scale of construction frequently overwhelmed these efforts, leaving a lasting imprint on the landscape. Furthermore, the extraction of pozzolana, crucial for creating hydraulic concrete, presented its own set of environmental challenges. Pozzolana deposits were often located in volcanic regions, and their exploitation involved extensive digging and removal of overburdened material, further disrupting vegetation cover and contributing to soil instability. The processing of pozzolana, requiring crushing and grinding, likely generated dust pollution, impacting air quality in surrounding areas. While the precise extent of these impacts remains difficult to assess due to limited direct documentation, it is reasonable to infer that aqueduct construction significantly altered local ecosystems and contributed to landscape degradation across vast regions of the Roman Empire. The scale of Roman aqueduct construction demanded more than just practical skill. It required a systematization of engineering principles and surveying techniques. While individual builders undoubtedly possessed considerable expertise, their knowledge was often tacit, passed down through apprenticeship rather than formalized in written instruction. The emergence of figures like Vitruvius marks a shift toward codifying this understanding. Marcus Vitruvius Pollio, writing around the 1st century BCE, produced De Architectura, a treatise that became foundational for Roman and subsequent Western engineering thought. De Architectura is not simply a manual of construction. It represents an attempt to organize and articulate the principles underlying Roman building practices. Vitruvius addressed topics ranging from city planning and temple design to water supply and military machines. but his discussions on aqueducts and hydraulic engineering are particularly significant for understanding how Romans approached these complex projects. He detailed methods for surveying land, calculating gradients essential for maintaining consistent water flow, and selecting appropriate materials based on their properties. Vitruvius emphasized the importance of precise measurement and geometric calculations in ensuring structural stability and efficient operation, a marked departure from purely empirical approaches. His work provided a framework for training engineers and standardized practices across different regions of the empire. The treatise offered advice on seasonal upkeep, reflecting an understanding that aqueducts required ongoing maintenance to preserve water quality and flow rates. Vitruvius's emphasis on precise measurement extended to documenting existing aqueducts, likely for purposes of maintenance and replication. The De Architectura details surveying techniques used to establish gradients and assess structural integrity, reflecting a practical concern with ensuring long-term functionality. Analyses of carbonate deposits within Roman aqueducts have revealed repeated manual removal of calcite at intervals of 1 to 5 years, aligning with Vitruvius's advice on seasonal upkeep. These findings suggest that the principles outlined in De Architectura were not merely theoretical, but actively implemented by engineers and maintenance crews across the empire. Furthermore, Vitruvius's discussions of hydraulic gradients are now being informed by modern geomatic surveys applied to surviving aqueduct sections south of Rome. These measurements reconstruct original gradients and assess centuries of subsidence, enabling more accurate flow reconstructions. These geomatic surveys have enabled more accurate flow reconstructions and paved the way for future geodynamic studies of aqueduct deformation over millennia, contributing to a deeper understanding of both engineering practice and long-term structural behavior. Analysis of carbonate deposits within Roman aqueducts continue to reveal insights into past maintenance regimes. In southern France, these encrustations demonstrate repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socio-economic conditions. The Roman Empire's water management networks were extensive and sophisticated, relying centrally on aqueducts to deliver water to urban centers, military camps, and industrial sites. These channels conveyed spring and river water over considerable distances by exploiting precise gradients to maintain a steady, gravity-driven flow. The scale and consistency of this infrastructure underpinned urban growth, public hygiene, and socio-political cohesion. A key figure in the practical management of these aqueducts was Sextus Julius Frontinus, who served as curator aquarum, overseer of the water supply, for Rome during the reign of Emperor Nerva in the early 2nd century CE. His written work, De Aqueductu, provides a detailed account of his duties and offers insights into the practical challenges of maintaining such a complex system. The text is not a theoretical treatise on hydraulics. Rather, it's a manual outlining procedures for inspection, regulation, and repair. Frontinus describes assessing water flow rates, identifying sources of leakage or theft, and establishing schedules for maintenance work. He emphasized the importance of regular inspections to ensure equitable distribution among citizens and businesses who paid for access to the aqueduct system. Frontinus's detailed observations extended to identifying and addressing inefficiencies within the system. He documented instances of illegal connections, where individuals diverted water without authorization, diminishing supply for those paying for access. To combat this, he instituted stricter penalties and increased surveillance along the aqueduct routes. The De Aqueductu also reveals Frontinus's methodical approach to assessing the condition of the channels themselves. He described methods for measuring flow rates using calibrated vessels, allowing him to quantify losses due to leaks or blockages. Furthermore, his account highlights the importance of regular cleaning and repair work, noting that carbonate deposits, mineral crusts precipitated within the aqueducts, could impede water flow over time. Recent investigations into these very carbonate formations in southern France have shown repeated manual removal at intervals of 1 to 5 years, aligning with Frontinus's recommendations for seasonal upkeep. These analyses demonstrate a recurring need for maintenance and reflect changing socioeconomic conditions impacting resource management practices. These efforts to maintain water quality and flow rates extended beyond simple cleaning. Frontinus's observations also addressed the challenges posed by geological factors. He recognized that seismic activity could damage aqueduct structures, leading to leaks or collapses, necessitating repairs following ground movement. Analyses of carbonate deposits within Roman aqueducts have revealed new insights into both environmental history and maintenance regimes, demonstrating how aqueduct deposits serve as dual archives of paleoclimate and infrastructure events. The Roman Empire's water management systems were remarkable feats of engineering, relying heavily on aqueducts to deliver water to urban centers and other sites. These channels, often carried on arches or buried underground, exploited gravity to move water over considerable distances. Regular maintenance was integral to the system's success. Cleaning, inspection, and repair ensured both water quality and consistent flow rates. Recent investigations into carbonate crust formations within aqueducts have revealed a recurring need for upkeep. Analyses of incrustations in a southern French aqueduct show repeated manual removal of calcite at intervals of 1 to 5 years, mirroring the advice on seasonal maintenance found in historical texts. However, as the empire entered its later centuries, this careful regimen began to falter. The scale and consistency of Roman water infrastructure had previously underpinned urban growth, public hygiene, and socio-political cohesion. But shifting socio-economic conditions impacted resource management practices, leading to a decline in aqueduct maintenance. While the precise causes remain complex, it is evident that the dedication to upkeep diminished over time. The removal of calcite deposits, once performed regularly every 1 to 5 years, became less frequent, suggesting a reduction in available labor or resources dedicated to this task. This deterioration wasn't solely attributable to neglect. Geological factors also played a role. Seismic activity could damage aqueduct structures, leading to leaks and collapses that required repair. But the capacity to respond effectively appears to have lessened. The reduced frequency of calcite removal suggests a broader pattern of resource reallocation within the empire. While specific records detailing labor assignments are scarce, evidence from other sectors indicates a general decline in state investment across various public works projects. Geological instability further exacerbated these challenges. Seismic activity caused structural damage requiring repair, but the capacity to respond effectively diminished. The precise nature of this diminished capacity remains unclear. It may have stemmed from logistical difficulties in transporting materials and personnel to affected areas, or a reduction in skilled engineers available for assessment and reconstruction. Furthermore, analyses of carbonate deposits within Roman aqueducts reveal that climatic shifts also contributed to maintenance demands. Variations in rainfall patterns could lead to increased sediment loads, necessitating more frequent cleaning of channels, while periods of drought might cause structural cracking due to ground subsidence. The interplay between these geological and climatic factors likely amplified the impact of any reduction in routine upkeep. The Roman aqueducts' legacy extends far beyond their role in supplying water to ancient cities. Modern engineers continue to draw inspiration from these remarkable feats of hydraulic engineering, recognizing and adapting principles that underpinned their success for centuries. The very concept of an aqueduct, a channel designed to convey water over long distances by gravity, remains fundamental to modern water management systems. Roman designs frequently employed arches, tunnels, or buried pipelines to achieve this, meticulously calculating gradients to maintain a steady flow across considerable distances. A particularly ingenious solution was the inverted siphon, a closed-pressure conduit used to transport water across valleys or depressions. The Romans constructed these siphons from stone, ceramic, and lead, confronting challenges of sealing, jointing, and air release with remarkable ingenuity techniques that inform contemporary best practices in pressure line construction. Recent studies have combined elevation surveys with hydraulic modeling to estimate flow rates within Roman pipelines, demonstrating a sophisticated understanding of how pipe diameter and surface roughness influence water distribution under gravity. Geometric measurement techniques applied to surviving aqueduct sections allow for the reconstruction of original gradients and assessment of centuries of subsidence, a process that informs modern efforts to understand and mitigate structural deformation in hydraulic infrastructure. These geometric surveys, alongside detailed analyses of carbonate deposits within aqueduct channels, offer a window into not only the infrastructure's construction, but also its operational history and environmental context. Investigations of incrustations in southern France, for example, reveal evidence of repeated manual removal of calcite at intervals ranging from 1 to 5 years, a practice aligning with textual advice on seasonal upkeep and reflecting shifting socio-economic conditions. Similarly, stable isotope records extracted from carbonate layers within a Turkish aqueduct channel have provided climatic and seismic chronologies corresponding to the reign of Nero, demonstrating that these structures serve as dual archives, documenting both infrastructure events and broader environmental shifts. The meticulous reconstruction of the Barbegal watermill complex in southern France, also utilizing carbonate incrustations, has illuminated bespoke flume designs and serial arrangements indicative of advanced hydraulic planning during the late Republican and early Imperial periods, Europe's first industrial-scale milling installation. These principles of hydraulic engineering, the careful consideration of gradient, pipe diameter, and material properties, persist as fundamental tenets of modern water management. Studies of pipelines supplying public fountains in Pompeii, for example, have combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second, illuminating how these factors controlled distribution under gravity. Similarly, a comprehensive review of Roman pressure conduits has detailed the design of inverted siphons constructed from stone, ceramic, and lead, describing solutions to sealing, jointing, and air release challenges, techniques that continue to inform contemporary engineering practice. The scale and consistency of Roman water infrastructure underpinned urban growth, public hygiene, and socio-political cohesion. Beyond simply delivering water, Romans harnessed hydraulic power through watermills, using overshot and undershot wheels to drive grain mills and other industries. But the very structures that enabled this technological prowess, the aqueducts themselves, present a continuing puzzle for modern engineers, their remarkable durability. Many Roman aqueducts have survived millennia of weathering, earthquakes, and neglect, exhibiting an unexpected resistance to erosion that has prompted considerable scientific investigation. Recent investigations into carbonate crusts within these aqueducts are revealing new insights into both environmental history and maintenance regimes. Analyses of incrustations in a southern French aqueduct, for example, show repeated manual removal of calcite at intervals of 1 to 5 years. This practice aligns with textual advice on seasonal upkeep and reflects shifting socio-economic conditions. The longevity of Roman concrete has become a focal point within this research, as engineers seek to understand the mechanisms contributing to its resilience. One key element under scrutiny is the presence of what the Romans termed pozzolana. The term pozzolana refers to volcanic ash, specifically from Mount Vesuvius and other sites near Rome. When mixed with lime during concrete production, it created a material exhibiting remarkable properties. Modern analysis reveals that this pozzolanic reaction generated calcium aluminum silicate hydrate (CaSH) gel, which significantly strengthened the concrete matrix. Furthermore, seawater exposure appears to have fostered further strengthening through ongoing chemical reactions. The presence of chloride ions from the sea initiated a process where the CaSH gel continued to form and consolidate over time, effectively self-healing cracks and increasing density. This contrasts sharply with modern Portland cement concretes, which often degrade under similar conditions. Studies examining pipelines supplying Pompeii's public fountains have also contributed to this understanding, illuminating how pipe diameter and surface roughness control distribution under gravity. This ongoing investigation into Roman concrete's durability has also benefited from detailed examination of carbonate deposits within aqueducts themselves. These mineral crusts, primarily calcite, precipitated inside the channels and serve as archives of both environmental conditions and structural history. High-resolution records extracted from these layers have provided chronologies extending back to the reign of Nero, demonstrating how such deposits can reflect climatic shifts and even seismic events impacting infrastructure. Analyses of incrustations in a southern French aqueduct reveal that these formations offer insights into maintenance regimes. Specifically, they show repeated manual removal of calcite at intervals of 1 to 5 years. The Roman Empire's water management networks were extensive and sophisticated, relying heavily on aqueducts to deliver water over considerable distances. These channels typically exploited gravity, maintaining a steady flow through arches, tunnels, or buried pipelines. However, valleys presented a significant challenge to this gravity-driven system. To overcome these topographical obstacles, the Romans developed what they termed inverted siphons. An inverted siphon is essentially a closed pressure conduit used to transport water across depressions. Rather than relying on a continuous downward slope, it utilizes hydraulic head, the potential energy of water due to its elevation, to force water over and through a lower point in the landscape. The system involves 2 elevated points, connected by descending pipes. Water flows down into a low point, creating pressure that then pushes it back up the other side, effectively siphoning across the valley floor. These conduits were constructed from various materials, including stone, ceramic, and lead, reflecting available resources and engineering expertise. Roman engineers addressed challenges inherent in such systems, sealing joints, managing air release, and ensuring structural integrity, drawing on established best practices documented in treatises like Vitruvius's writings. The materials used, stone, ceramic, and lead, presented distinct challenges for construction and longevity. Stone conduits required skilled stonemasons to shape and fit blocks precisely, ensuring a watertight seal. Ceramic pipes, while lighter than stone, were susceptible to breakage during transport and installation. Lead's malleability facilitated complex bends and joints, but raised concerns about potential contamination of the water supply, though this appears not to have been a primary consideration at the time. Roman engineers recognized that air pockets within these inverted siphons could disrupt flow, creating vacuums or allowing backflow. To mitigate this, they incorporated strategically placed air vents, small openings along the conduit's length to allow trapped air to escape and water to enter, maintaining consistent pressure. Vitruvius's writings detail methods for jointing and sealing these pressure lines, emphasizing the importance of careful workmanship to prevent leaks and maintain hydraulic efficiency. The precise design and placement of these components were crucial for reliable operation. A compromised seal or blocked vent could render the entire siphon ineffective. These inverted siphons frequently involve multiple chambers connected by short vertical drops and rises, a design dictated by the topography of the valleys they traversed. The precise number of these chambers varied depending on the depth of the valley and the desired hydraulic head. Roman engineers meticulously calculated these parameters to ensure consistent water flow and prevent catastrophic failure. Evidence suggests that some siphons incorporated inspection shafts at regular intervals along their length, allowing for visual assessment of conduit condition and facilitating maintenance interventions. The construction of these structures demanded a high degree of coordination between various craftspeople, stonemasons, ceramicists, lead workers, and laborers, each contributing specialized skills to the overall project. The Aqua Appia completed in 312 BC, holds a place as Rome's first aqueduct. It was sponsored by censor Appius Claudius Caecus, who is also known for initiating construction of the Appian Way, one of Rome's earliest major roads. Unlike later Roman aqueducts that incorporated impressive above-ground arches, the Aqua Appia ran almost entirely underground. This design reflected a deliberate choice to minimize visual impact and integrate the structure into the existing landscape. The construction process began with careful planning and route selection. To excavate the channels, workers dug shafts, putae, at intervals of roughly 230 feet. These shafts served as access points for removing earth and lowering building materials. Stone blocks were lowered using cranes to line the tunnel walls. Bricks or concrete were sometimes used depending on local availability. A waterproof layer of opus sigillum, a mortar composed of crushed tiles and amphorae fragments, was applied to the channel lining. This ensured that the water remained as pure as possible during its journey. The route itself often required significant detours, following the land's natural grade whenever feasible. The undertaking demanded considerable resources and manpower. Evidence suggests that workers included slaves alongside free laborers. Maintaining these underground channels presented ongoing challenges. Specialized personnel, aquarii, were responsible for repairs and cleaning to prevent blockages and preserve water quality. These aquarii ensured the channel remained covered, and tanks called piscinae limeriae were positioned along the route to decant impurities from the flowing water. The construction process itself presented considerable challenges beyond simple excavation and lining. The funerary monument of Nonius Datus, found at Béjaïa in Algeria, details some of these difficulties. According to this inscription, teams excavating sections of a tunnel did not meet where planned, requiring adjustments to the route. Furthermore, bandits attacked the construction site, forcing engineers like Datus to flee for their safety. These accounts suggest that even with careful planning, unforeseen obstacles frequently disrupted progress and demanded adaptability from those involved in building the aqueducts. Maintaining these underground channels also required ongoing effort. Specialized personnel, aquarii, were responsible for repairs and cleaning to prevent blockages and preserve water quality. They ensured the channel remained covered, and tanks called piscinae limeriae were positioned along the route to decant impurities from the flowing water. The monument also notes that Datus's team had to adjust their route due to unforeseen geological conditions, a testament to the challenges of subterranean construction. The inscription details how workers used simple tools, picks, shovels, and baskets, to remove earth and rock, relying on manual labor for nearly every stage of the process. While the monument does not specify the precise methods employed in waterproofing the channels, it implies that this was an ongoing concern requiring constant attention from the aquarii. The text highlights Datus's personal involvement in overseeing these repairs, suggesting a level of direct responsibility uncommon among Roman officials. The Aqua Claudia stands as a testament to Roman engineering ambition. Completed between AD 38 and 52, it was part of Caligula's effort to meet Rome's escalating water demands. The aqueduct stretched an impressive 69 kilometers, roughly 42 miles, from its source near Praeneste to the city itself. This length alone underscores the scale of the undertaking, a continuous line traversing the landscape, demanding constant maintenance and adaptation. The structure incorporated numerous arches, though precise numbers are not recorded in available sources. These arched sections were necessary to bridge valleys and uneven terrain along the route, representing only a fraction of the total distance. The majority of the Aqua Claudia's path ran either underground or along ground-level channels. To put this into perspective, Rome was supplied by aqueducts totaling 315 miles in length. 269 miles of that were subterranean, and just under 12%, roughly 36 miles, consisted of arched structures. The sheer volume of water the Aqua Claudia delivered to Rome highlights its vital role in sustaining the city's population, which was estimated at 1 million people in the 1st century AD. This quantity helped supply not only drinking water, but also the elaborate public fountains and baths that defined Roman urban life. The construction itself required a massive workforce, utilizing techniques inherited from earlier Mediterranean cultures while innovating with Roman engineering practices. Workers excavated channels using picks, shovels, and baskets, a labor-intensive process reliant on manual power for nearly every stage of construction. The Aqua Claudia's construction involved a substantial workforce, and evidence suggests that maintaining it required an ongoing commitment of personnel. A Roman treatise, found at Bijaya in Algeria, details the experiences of one engineer, Nonius Datus, who oversaw its creation around AD 152. The text recounts challenges encountered during the project's execution, including discrepancies between excavation teams and attacks by bandits. These accounts underscore that construction was not a straightforward process, but involved overcoming logistical and security concerns. Furthermore, specialized workers known as aquarii were responsible for the aqueduct's operation and cleanliness. These technicians performed repairs and cleared blockages to maintain water quality. The channels themselves were kept covered, and settling tanks, piscinae limaria, were strategically placed along the route to remove impurities. Sextus Julius Frontinus, writing in the 1st century AD, noted instances of plumbing fraud where individuals attempted to illegally access or siphon off water from the aqueducts, highlighting the need for regulation and oversight even during operation. The Pont du Gard stands as a particularly striking example of Roman engineering prowess. This structure, part of the broader aqueduct system supplying water to Nemausus, modern Nimes, demonstrates a remarkable level of precision in its design and construction. The aqueduct itself exploited precise gradients to maintain a steady flow of water over considerable distances, as noted in descriptions of Roman water management systems. The Pont du Gard's most distinctive feature is its three-tiered arch system. This arrangement allowed the structure to span the Garden River Valley, while also providing support for the channel that carried the water above. The lower tier consists of 16 arches, followed by an 11-arch middle tier and a 6-arched upper tier. The sheer scale of these arches is impressive. Each block was carefully shaped and fitted together with minimal mortar, a testament to the skill of Roman masons. Analyses of carbonate crusts within this southern French aqueduct reveal repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socioeconomic conditions and demonstrating ongoing maintenance efforts. The structure's design wasn't simply about aesthetics, it was fundamentally linked to maintaining a consistent hydraulic gradient that drove the water flow. This gradient ensured gravity would propel the water along its course with predictable efficiency. The careful arrangement of these arches was not arbitrary. It reflects a deliberate response to the topography and structural demands of the site. The varying arch sizes likely serve to distribute weight effectively across different sections of the valley, accommodating changes in elevation and ground conditions. Analyses utilizing geomatic measurement techniques have been applied to surviving aqueduct sections south of Rome, employing high-precision leveling to reconstruct original gradients and assess centuries of subsidence. These surveys enabled more accurate flow reconstructions and paved the way for future geodynamic studies of aqueduct deformation over millennia. The construction process itself involved a complex logistical undertaking, requiring quarrying substantial amounts of stone, primarily limestone, and transporting it to the site. Roman engineers employed ramps and levers to raise the massive blocks into position, demonstrating an understanding of mechanical advantage. Furthermore, research from Nature Portfolio indicates that repeated manual removal of calcite within this southern French aqueduct occurred at intervals of 1 to 5 years, reflecting shifting socio-economic conditions and ongoing maintenance efforts. The logistical undertaking extended to quarrying specialized tools for stone dressing and shaping, including iron chisels and wedges. These implements facilitated the extraction of precisely sized blocks from the limestone bedrock. Geomatic surveys applied to aqueduct sections south of Rome reveal that variations in construction quality also occurred across different segments, potentially reflecting changes in workforce composition or resource availability over time. Research indicates that carbonate layers within these structures provide dual archives of paleoclimate and infrastructure events, demonstrating their utility beyond simple water conveyance. The Roman aqueducts were more than just channels conveying water. They represented a vast logistical undertaking reliant on substantial labor. While engineering principles guided their design, the physical construction demanded an immense workforce engaged in quarrying, shaping stone, and moving materials across challenging terrain. The scale of this effort is underscored by research indicating that carbonate layers within aqueduct structures provide archives of both environmental history and infrastructure maintenance regimes. The process began with quarrying limestone bedrock to supply the blocks needed for arches, tunnels, and buried pipelines. These laborers employed iron chisels and wedges to extract precisely sized stones from the quarries. Once extracted, these materials had to be transported, sometimes over considerable distances, to construction sites. The precise composition of this workforce remains a subject of ongoing investigation. However, it's clear that their efforts were essential to realizing the aqueduct's design. Geomatic surveys reveal variations in construction quality along different segments of aqueducts south of Rome, suggesting fluctuations in workforce size or skill levels over time. The techniques used by these laborers involved a combination of manual effort and rudimentary tools. The creation of inverted siphons, closed-pressure conduits vital for crossing valleys, required skilled stonemasons, ceramicists, and lead workers to address challenges related to sealing joints and releasing trapped air. These solutions drew upon established best practices detailed in Vitruvian treatises. High-precision leveling techniques applied to surviving aqueduct sections have enabled reconstruction of original gradients, demonstrating the meticulousness required in ensuring a consistent gravity-driven flow over many kilometers. The creation of inverted siphons, closed-pressure conduits vital for crossing valleys, required skilled stonemasons, ceramicists, and lead workers to address challenges related to sealing joints and releasing trapped air. These solutions drew upon established best practices detailed in Vitruvian treatises. High-precision leveling techniques applied to surviving aqueduct sections have enabled reconstruction of original gradients, demonstrating the meticulousness required in ensuring a consistent gravity-driven flow over many kilometers. Studies examining pipelines supplying public fountains in Pompeii combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second. These measurements illuminate how pipe diameter and surface roughness control distribution under gravity. Analyses of incrustations within a southern French aqueduct revealed repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socio-economic conditions. Analyses of incrustations within a southern French aqueduct revealed repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socio-economic conditions. These interventions highlight an ongoing commitment to maintaining water quality and flow capacity throughout the aqueduct's operational life. Research into Roman pressure lines details design solutions for inverted siphons constructed from stone, ceramic, and lead, addressing challenges related to sealing joints and releasing trapped air by drawing upon established best practices detailed in Vitruvian treatises. The Roman Empire's water management networks were among the most extensive and sophisticated of the pre-industrial world, with aqueducts serving as a central component. These engineered channels delivered spring and river water to urban centers, military camps, and industrial sites, exploiting precise gradients to maintain a steady gravity-driven flow over considerable distances. The scale and consistency of this infrastructure underpinned urban growth, public hygiene, and socio-political cohesion. Beyond simply supplying water, Romans harnessed hydraulic power through water mills. These mills employed both overshot and undershot wheels to drive grain mills, workshops, and other industries. Maintaining these channels and mills was vital. Cleaning, inspection, and repair preserved water quality and flow rates. The Barbegal complex in France, for example, reconstructed using carbonate encrustations, reveals a bespoke flume design and serial arrangement that formed Europe's first industrial-scale milling installation. This highlights advanced hydraulic planning in late Republican and early imperial engineering. The impact extended to urban development itself. Studies of the pipelines supplying Pompeii's public fountains combined elevation surveys with hydraulic modeling to estimate flow rates, demonstrating how pipe diameter and surface roughness controlled distribution under gravity. The presence of these systems facilitated denser populations and more complex social structures within cities. Regular maintenance was essential for ensuring functionality. Analyses of incrustations in a southern French aqueduct show repeated manual removal of calcite at intervals of 1 to 5 years. Reflecting shifting socio-economic conditions, the impact extended to urban development itself. Studies of the pipelines supplying Pompeii's public fountains combined elevation surveys with hydraulic modeling to estimate flow rates, demonstrating how pipe diameter and surface roughness controlled distribution under gravity. The presence of these systems facilitated denser populations and more complex social structures within cities. Regular maintenance was essential for ensuring functionality. Analyses of incrustations in a southern French aqueduct show repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socio-economic conditions. These deposits also provide environmental records, with stable isotope analysis revealing climatic and seismic events during the reign of Nero. Research into Roman water transport details designs for inverted siphons constructed from stone, ceramic, and lead, addressing challenges in sealing and air release. Geomatic measurements applied to aqueduct sections south of Rome have enabled reconstruction of original gradients and assessment of subsidence over time, contributing to more accurate flow reconstructions. These geomatic measurements also facilitated assessments of subsidence over time, revealing localized ground movements that impacted aqueduct gradients and flow efficiency. Studies examining pipelines supplying Pompeii's public fountains have quantified flow rates between 0.1 and 2.5 liters per second, demonstrating how pipe diameter and surface roughness influenced distribution under gravity. The design of inverted siphons, constructed from stone, ceramic, and lead, addressed challenges in sealing and air release, as detailed in reviews of Roman water transport practices. The Roman Empire's water management systems, central to its urban growth and socio-political cohesion, relied heavily on aqueducts, engineered channels delivering water over considerable distances by gravity. These structures, employing inverted siphons for crossings and castellums for distribution, maintained flow rates quantified between 0.1 and 2.5 liters per second, influenced by pipe diameter and surface roughness. However, the longevity of this infrastructure was not indefinite. The decline of the Roman Empire initiated a period where the consistent maintenance that underpinned these systems began to falter. The scale of aqueduct upkeep demanded resources, labor, materials, and administrative oversight that became increasingly strained as imperial authority weakened. Research into carbonate crusts within aqueducts reveals repeated manual removal of calcite at intervals of 1 to 5 years, a practice reflecting shifting socio-economic conditions. This suggests that even during periods of relative stability, maintenance was not always consistent or optimal, and any disruption would have had significant consequences for water supply. As the Western Roman Empire fragmented, the centralized authority responsible for coordinating such widespread infrastructure projects diminished. Local control often replaced imperial direction, leading to inconsistent priorities and a gradual neglect of aqueduct repair and cleaning. The consequences extended beyond simple neglect. As imperial authority diminished, so too did the capacity to levy taxes and conscript labor for public works. The maintenance of aqueducts, once a visible demonstration of Roman power and prosperity, became an increasingly burdensome expense for smaller, fragmented polities. Analyses of carbonate deposits within aqueducts reveal shifts in removal intervals, reflecting these changing socio-economic conditions. While earlier periods might have seen consistent cleaning every 1 to 5 years, later intervals grew more irregular, indicating reduced resources or competing priorities. The disruption of trade routes further exacerbated the situation, limiting access to materials like lead for pipe repairs and stone for structural reinforcement. This scarcity compounded the challenges faced by local administrators attempting to maintain even basic functionality. While some communities continued localized repair efforts, these were often reactive rather than preventative, addressing immediate failures instead of proactively safeguarding against future deterioration. The disruption of trade routes further exacerbated the situation, limiting access to materials like lead for pipe repairs and stone for structural reinforcement. This scarcity compounded the challenges faced by local administrators attempting to maintain even basic functionality. While some communities continued localized repair efforts, these were often reactive rather than preventative, addressing immediate failures instead of proactively safeguarding against future deterioration. Analyses of carbonate deposits reveal that the intervals between cleaning diminished further in many regions, suggesting a shift from periodic maintenance to merely preventing catastrophic failure. The nature of the repairs also changed. Evidence indicates an increased reliance on readily available materials and simpler techniques, often resulting in less durable solutions compared to earlier Roman engineering standards. These alterations reflect both economic constraints and a decline in specialized craftsmanship as skilled artisans migrated or were otherwise unavailable. The decline of Roman aqueducts did not erase their influence. Rather, it laid a foundation for future water management practices. The very principles that guided Roman engineers, the exploitation of gravity through precisely graded channels, the ingenious use of inverted siphons to navigate valleys, and the careful regulation of flow with settling basins and distribution systems would resonate across centuries. Modern water engineering owes a considerable debt to these innovations. Studies combining elevation surveys and hydraulic modeling have even allowed researchers to estimate historical flow rates in Roman pipelines, demonstrating an understanding of pipe diameter and surface roughness that controlled distribution under gravity. The enduring legacy extends beyond mere design. The Romans' emphasis on regular maintenance, the periodic cleaning of channels, inspection for damage, and prompt repair represented a holistic approach to infrastructure management. Recent investigations into carbonate crusts within aqueducts reveal evidence of this practice. Analyses in southern France show repeated manual removal of calcite at intervals of 1 to 5 years, reflecting advice on seasonal upkeep. The meticulous record-keeping embedded within these deposits, as demonstrated by stable isotope records from a Turkish aqueduct channel providing climatic and seismic chronologies for the reign of Nero, highlights an understanding that infrastructure events could be preserved in geological layers. The meticulous record-keeping embedded within these deposits, as demonstrated by stable isotope records from a Turkish aqueduct channel providing climatic and seismic chronologies for the reign of Nero, highlights an understanding that infrastructure events could be preserved in geological layers. This capacity to encode historical information within seemingly inert structures underscores the Romans' sophisticated approach to engineering and their awareness of long-term durability. Further investigation into carbonate deposits has revealed bespoke flume designs at the Barbagal watermill complex, Europe's first industrial-scale milling installation, demonstrating advanced hydraulic planning in late Republican and early imperial engineering. Studies utilizing geomatic measurement techniques have also been applied to surviving aqueduct sections south of Rome. High-precision leveling allowed for reconstruction of original gradients and assessment of centuries of subsidence, enabling more accurate flow reconstructions. These surveys furthered understanding of how aqueducts deformed over millennia. These geomatic surveys have furthered understanding of how aqueducts deformed over millennia. Analyses of incrustations in Roman aqueducts have also illuminated maintenance regimes, revealing repeated manual removal of calcite at intervals of 1 to 5 years, matching textual advice on seasonal upkeep and reflecting shifting socioeconomic conditions. Investigations into pipelines supplying public fountains in Pompeii combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second, illustrating how pipe diameter and surface roughness controlled distribution under gravity. The aqueducts that supplied Roman cities were remarkable feats of engineering, but their longevity also depended on the materials used to construct them. While much attention is given to the arches and channels themselves, the concrete employed in their construction, particularly within tunnels and vaults, holds a unique story about Roman ingenuity. This wasn't simply a mixture of aggregate and binder. It was a carefully formulated material with properties that would later be lost to history, yet have recently begun to yield their secrets. Roman concrete differed significantly from earlier Greek concrete, which relied primarily on pozzolanic ash for setting. The Romans incorporated volcanic aggregates, specifically pozzolana, into their mixtures, creating a composite material. This pozzolana reacted with lime in the presence of water, forming calcium silicate hydrate, CSH, the primary binding agent in cement and concrete. Analyses of carbonate crusts within Roman aqueducts have revealed new insights into both environmental history and maintenance regimes. These deposits served as archives of past conditions, recording climatic shifts and even seismic events. The specific composition varied depending on local availability. For example, a southern French aqueduct showed repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socioeconomic conditions impacting upkeep practices. The varying composition of Roman concrete reflected both resource availability and evolving construction techniques over time. Early concrete often incorporated volcanic ash from sites like Pozzuoli near Naples, which provided a particularly reactive pozzolana. Later formulations experimented with different aggregate types, including crushed brick and ceramic fragments, evidence of recycling practices within urban centers. Analyses have revealed that the ratio of lime to pozzolanic material also shifted over time, potentially influenced by fluctuations in raw material costs or changes in desired concrete properties. The presence of air bubbles within Roman concrete has been noted. These voids, initially considered flaws, may actually have contributed to its durability by providing space for expansion and contraction due to thermal stress. Furthermore, the ongoing reaction between the lime and pozzolana continued long after construction, a process that strengthened the material over decades and even centuries, a phenomenon largely absent in modern concrete production. The presence of air bubbles within Roman concrete has been noted. These voids, initially considered flaws, may actually have contributed to its durability by providing space for expansion and contraction due to thermal stress. Furthermore, the ongoing reaction between the lime and pozzolana continued long after construction, a process that strengthened the material over decades and even centuries, a phenomenon largely absent in modern concrete production. Recent investigations into carbonate crusts within aqueducts have revealed new insights into both environmental history and maintenance regimes. Analyses of incrustations indicate variations in aggregate size and composition across different regions and time periods, suggesting localized adaptations to available resources and evolving construction practices. The Roman Empire's influence extends far beyond its political and military achievements. It also left an indelible mark on engineering, particularly through its sophisticated water management systems. These networks were central to the empire's success, comprising aqueducts that delivered spring and river water to urban centers, military camps, and industrial sites. The structures themselves exploited precise gradients to maintain a steady flow over considerable distances, often carried on arches or within tunnels and buried pipelines. Where valleys presented an obstacle, inverted siphons conveyed water under pressure. Beyond simple delivery, Romans harnessed hydraulic power through watermills, utilizing both overshot and undershot wheels for grain mills and workshops. The importance of water in Roman society was multifaceted. Public baths were a cornerstone of daily life, requiring substantial volumes of clean water. Sanitation systems also relied on consistent water supply to manage waste and maintain public hygiene. The scale and reliability of this infrastructure directly underpinned urban growth and contributed to socio-political cohesion. Maintenance was as vital as initial construction. Regular cleaning, inspection and repair ensured both water quality and flow rates remained adequate for these diverse needs. Analyses of incrustations within a southern French aqueduct reveal repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socio-economic conditions and adherence to established upkeep practices. The consistent delivery of water also profoundly shaped urban planning and architectural design. Public fountains, often elaborately constructed with marble or carved stone, served as focal points within Roman cities, providing accessible drinking water for citizens and livestock alike. The distribution networks supplying these fountains, as evidenced by studies in Pompeii, maintained flow rates ranging from 0.1 to 2.5 liters per second, demonstrating a deliberate engineering approach to ensure adequate supply under gravity. Furthermore, the construction of pressure conduits, sometimes utilizing stone, ceramic, or lead, required sophisticated solutions for sealing joints and releasing trapped air, reflecting an understanding of hydraulic principles documented in Vitruvian treatises. Investigations into surviving aqueduct sections south of Rome have employed geomatic measurement techniques to reconstruct original gradients, revealing centuries of subsidence and enabling more accurate flow reconstructions. These surveys also offer potential avenues for future studies examining the long-term deformation of these structures due to geological shifts. The deliberate engineering approach extended to sanitation as well. Roman cities incorporated extensive sewer systems, often utilizing gravity-fed channels, similar in construction to aqueducts, but designed for waste removal rather than water delivery. Investigations of these networks, alongside analyses of sediment deposits within them, offer insights into urban hygiene practices and the management of refuse. The Roman aqueducts, celebrated for their scale and ingenuity, were not static monuments, but required constant attention to remain functional. The very materials they were constructed from, stone, brick, lead, and concrete, were susceptible to natural decay over time. Water itself contributed to this deterioration. The dissolved minerals within it precipitated as carbonate crusts inside channels, gradually reducing flow capacity. Investigations of aqueducts in southern France have revealed evidence of repeated manual removal of these calcite deposits, occurring at intervals of 1 to 5 years. This upkeep reflected both practical necessity and shifting economic conditions. Beyond material degradation, human neglect played a significant role in the decline of many aqueduct systems. While regular maintenance was recognized as vital, as noted in contemporary writings, periods of political instability or economic hardship could lead to reduced investment in repairs. The accumulation of sediment within channels also posed an ongoing challenge, requiring periodic clearing to maintain efficient water flow. Furthermore, seismic activity presented a constant threat. High-resolution records from carbonate layers within a Turkish aqueduct channel have even provided chronologies for the reign of Nero, demonstrating how these deposits can record infrastructure events like earthquakes. These challenges were not always addressed with equal vigor across the Roman Empire, and regional variations in maintenance practices are evident. For instance, aqueducts supplying larger urban centers generally received more consistent attention than those serving smaller settlements or military outposts. The degree of preservation also varied based on local geological conditions. Areas prone to earthquakes or landslides experienced accelerated deterioration requiring frequent reconstruction. Studies examining the Roman aqueduct of Patara in southwestern Turkey have demonstrated how carbonate deposits within the channel record seismic events from Nero's reign, illustrating a direct link between natural disasters and infrastructure damage. Furthermore, shifts in land use patterns following periods of decline could exacerbate existing problems. As populations fluctuated or agricultural practices changed, aqueducts might be repurposed for irrigation or other uses, sometimes leading to modifications that compromised their structural integrity or reduced water quality. The abandonment of sections of the aqueduct network also resulted in localized silting and vegetation overgrowth, further hindering functionality. These shifts often resulted in localized silting and vegetation overgrowth, further hindering functionality. Analyses of incrustations within a southern French aqueduct demonstrate repeated manual removal of calcite at intervals of 1 to 5 years, reflecting shifting socioeconomic conditions. This ongoing intervention highlights that even seemingly robust infrastructure required consistent human effort for sustained operation. The Roman Empire's expansion across a vast territory necessitated increasingly sophisticated methods of water management. Prior to large-scale infrastructure projects, communities relied on local springs and rivers for their needs. However, as urban centers grew in size and population density, these sources proved inadequate, spurring the development of more extensive systems. Early aqueducts were relatively simple channels designed to convey water from nearby sources to settlements. These initial efforts gradually evolved into complex networks that spanned considerable distances, exploiting gravity to deliver water over many kilometers. The structures themselves varied. Some were engineered as arches, others tunneled through hillsides, and still others constructed as buried pipelines. A key innovation was the inverted siphon, a closed-pressure conduit used to transport water across valleys or depressions. These siphons utilized hydraulic head to overcome changes in elevation, demonstrating a growing understanding of fluid dynamics. Furthermore, Romans harnessed hydraulic power by constructing water mills that employed overshot and undershot wheels to drive various industrial processes, including grain milling and textile production. The Barbe-Gaulle complex in France, reconstructed through analysis of carbonate encrustations, exemplifies this advanced engineering. It comprised 16 overshot wheels arranged serially, representing what is considered Europe's first industrial-scale milling installation. Maintaining these systems was crucial. Analyses of incrustations within Roman aqueducts reveal repeated manual removal of calcite at intervals of 1 to 5 years, a testament to the ongoing human effort required for sustained operation and reflecting shifting socioeconomic conditions. These maintenance efforts extended beyond simple debris removal. Studies of pipelines supplying Pompeii's public fountains have combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second, illuminating how pipe diameter and surface roughness control distribution under gravity. Roman engineers also addressed the challenges inherent in traversing valleys or depressions through the design of inverted siphons constructed from stone, ceramic, and lead. Vitruvian treatises provide context for understanding ancient best practices in pressure line construction, detailing solutions to sealing, jointing, and air release issues. Furthermore, geomatic measurement techniques applied to surviving aqueduct sections south of Rome have utilized high-precision leveling to reconstruct original gradients and assess centuries of subsidence, enabling more accurate flow reconstructions and paving the way for future studies of structural deformation. These geomatic surveys also contribute to understanding regional subsidence patterns over extended periods, providing a framework for assessing long-term structural stability and informing contemporary infrastructure planning. Analyses of carbonate deposits within aqueduct channels have yielded high-resolution stable isotope records, offering climatic and seismic chronologies extending back to the reign of Nero, demonstrating how these structures serve as dual archives of both paleoclimate and infrastructural events. The Roman Empire's water management networks represent one of the most extensive and sophisticated systems developed before industrialization. Central to this infrastructure were aqueducts, engineered channels designed to deliver spring and river water to urban centers, military camps, and industrial sites. These structures utilized precise gradients to maintain a steady gravity-driven flow over considerable distances. At challenging crossings, inverted siphons conveyed water under pressure across valleys. The construction and maintenance of these aqueducts required skilled engineers. While the term engineer, as we understand it today, didn't exist in Roman society, individuals possessing expertise in surveying, hydraulics, and construction played a vital role. Their responsibilities extended beyond initial building. Regular upkeep was essential for preserving water quality and flow rates. This included cleaning channels, conducting inspections, and performing necessary repairs. Recent investigations into carbonate crusts within aqueducts have revealed insights into both environmental history and these maintenance regimes, showing repeated manual removal of calcite at intervals of 1 to 5 years. The individuals responsible for these aqueducts held varied positions within Roman society, and their status reflected both technical skill and social standing. While not a formally defined profession, expertise in surveying hydraulics and construction was often associated with freedmen or members of the equestrian order, those who had amassed wealth but were not part of the senatorial class. Some engineers served as public officials, appointed by magistrates to oversee specific projects. Others worked under private patronage, contracted for building ventures commissioned by wealthy landowners or industrialists. The scale of aqueduct construction frequently demanded collaboration between these different groups. A magistrate might authorize a project and provide resources, while an engineer directed the labor force and ensured technical execution. Evidence from studies of Roman mills suggests that hydraulic planning reached advanced levels, with bespoke flume designs and serial arrangements employed in installations like the Barbagal watermill complex. This demonstrates a sophisticated understanding of fluid dynamics beyond simple conveyance. The collaboration often extended to incorporating local expertise. Communities along aqueduct routes possessed intimate knowledge of terrain and water sources, which proved invaluable during construction and maintenance. Studies examining pipelines supplying Pompeii's public fountains have combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second, illuminating how pipe diameter and surface roughness controlled distribution under gravity. This demonstrates a practical understanding of the relationship between infrastructure design and water delivery efficiency. Furthermore, evidence suggests that Roman engineers adapted their designs based on site-specific conditions. Reconstruction of the 2nd century Barbagal watermill complex employed carbonate encrustations to model a series of 16 overshot wheels, uncovering bespoke flume designs reflecting localized hydraulic planning. The Roman Empire's water management networks stand as a testament to engineering ingenuity, and their influence resonates even within modern urban planning and water distribution systems. Central to these networks were aqueducts, engineered channels designed to deliver spring and river water to cities, military camps, and industrial sites. These structures exploited precise gradients to maintain a steady gravity-driven flow over considerable distances. At challenging crossings, inverted siphons conveyed water under pressure across valleys, while settling basins and distribution systems regulated delivery to public baths, fountains, and private homes. The principles guiding Roman aqueduct design continue to inform contemporary practices. Studies of pipelines supplying Pompeii's public fountains have combined elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second. This demonstrates a practical understanding of how pipe diameter and surface roughness control distribution under gravity, a principle still applied in modern pipeline design. Furthermore, the use of inverted siphons, closed-pressure conduits used to transport water across depressions, remains a standard solution for navigating uneven terrain in contemporary infrastructure projects. A comprehensive review details their construction using stone, ceramic, and lead, addressing challenges like sealing and air release, issues that engineers still grapple with today. The application of geomatic measurement techniques to surviving aqueduct sections south of Rome has enabled more accurate flow reconstructions and paved the way for future geodynamic studies of aqueduct deformation over millennia. These surveys, employing high-precision leveling, allow researchers to reconstruct original gradients and assess centuries of subsidence impacting these structures. Such detailed analysis contributes to a deeper understanding of both the engineering principles at play and the long-term interaction between infrastructure and geological processes. Investigations into carbonate crusts within Roman aqueducts have also yielded valuable insights. Analyses of incrustations in a southern French aqueduct, for example, reveal repeated manual removal of calcite at intervals of 1 to 5 years. A practice consistent with textual advice on seasonal upkeep. These deposits serve as archives reflecting shifting socio-economic conditions and maintenance regimes. These geomatic surveys have also informed investigations into the pipelines supplying Pompeii's public fountains, combining elevation surveys with hydraulic modeling to estimate flow rates between 0.1 and 2.5 liters per second. Illuminating how pipe diameter and surface roughness control distribution under gravity. A comprehensive review of Roman pressure conduits details the design of inverted siphons constructed from stone, ceramic, and lead, describing solutions to sealing, jointing, and air release challenges. Recent investigations into carbonate crusts within Roman aqueducts have revealed new insights into both environmental history and maintenance regimes. Analyses of incrustations in a southern French aqueduct show repeated manual removal of calcite at intervals of 1 to 5 years, matching textual advice on seasonal upkeep. This practice reflects shifting socio-economic conditions. These mineral deposits, primarily calcite, are forming what researchers term carbonate deposits, acting as archives of the past. Beyond their role as indicators of maintenance practices, these carbonate layers have also provided unexpected information about the environment and geological activity surrounding the aqueducts. High-resolution stable isotope records from carbonate layers in a Turkish aqueduct channel have yielded climatic and seismic chronologies for the reign of Nero. This demonstrates how these deposits can serve as dual archives, preserving both environmental data and evidence of infrastructure events. The very process by which water flows through, precipitates minerals, and leaves behind layered records, provides scientists with a unique window into Roman engineering and its interaction with natural forces. These carbonate deposits also offer clues about the durability of Roman concrete itself. Recent analyses suggest that the continual interaction between flowing water and the calcium hydroxide within the concrete contributes to a self-healing mechanism. The water dissolves some of this calcium hydroxide, which then reacts with carbon dioxide from the atmosphere to precipitate calcite, essentially rebuilding cracks as they form. This process is ongoing, evidenced by the layered structure of the deposits themselves, where newer calcite layers seal older fissures. While not preventing cracking entirely, This natural mineralization appears to significantly extend the lifespan of Roman aqueducts, compared to structures built with more conventional concrete formulations. The precise conditions required for this self-healing, including water flow rates, atmospheric carbon dioxide levels, and the initial composition of the concrete mix, remain subjects of ongoing investigation. Further complicating this self-healing process is the variability in Roman concrete formulations themselves. Evidence suggests that recipes differed significantly across regions and over time, impacting the availability of calcium hydroxide and other reactive components. The precise ratio of volcanic ash to lime, for example, would have influenced the degree of hydration and subsequent calcite precipitation. Analyses of carbonate deposits from pipelines supplying Pompeii's public fountains indicate a range of flow rates between 0.1 and 2.5 liters per second, suggesting variations in water availability and its potential contribution to mineralization. Reconstructions of the Barbergol watermill complex have also highlighted bespoke flume designs, implying localized adaptations to hydraulic conditions that likely affected mineral deposition patterns within the aqueducts themselves. The Roman Empire's water management networks were extensive and sophisticated, relying heavily on aqueducts to deliver water to urban centers, military camps, and industrial sites. These structures channeled spring and river water over considerable distances, exploiting gravity through arches, tunnels, or buried pipelines. While the engineering feats themselves demanded skilled labor, the construction process also involved a significant workforce of enslaved people. The scale of their involvement remains difficult to quantify precisely due to limitations in surviving documentation. However, it is clear that enslaved individuals formed a crucial component of the teams responsible for excavating channels, quarrying stone, and transporting materials. The aqueduct's routes often dictated challenging terrain, necessitating substantial excavation through rock or soil. This labor was frequently assigned to slaves who would use tools like picks, shovels, and levers to clear pathways for the channel beds and foundations of supporting arches. Quarrying operations, essential for sourcing building materials such as limestone and granite, also relied heavily on enslaved laborers. These individuals were tasked with extracting stone blocks from quarries, shaping them into precise forms, and preparing them for transport to construction sites. The physical demands of these tasks were immense, requiring long hours in often harsh conditions. While the Nature article does not detail specific demographics or numbers regarding the enslaved workforce involved in aqueduct projects, it is reasonable to infer that their contribution was substantial, given the scale of Roman infrastructure development and the widespread use of slave labor across various sectors of the economy. The arduous nature of this labor likely resulted in high mortality rates and injury among enslaved workers, although specific figures are unavailable within the existing documentation. The Nature article does not provide details regarding compensation or care for these individuals beyond their value as assets. Their contribution to aqueduct construction was inextricably linked to the broader Roman system of slavery, which provided a readily exploitable workforce for large-scale public projects. While some enslaved people may have possessed specialized skills that made them valuable in specific tasks such as stone carving or hydraulic calculations, the majority were likely engaged in physically demanding labor with little opportunity for advancement or respite. The reliance on slave labor also meant that aqueduct construction could be interrupted by revolts or escapes, although the Nature article does not address these occurrences directly. The reliance on slave labor also presented logistical challenges beyond potential disruption from revolt. The Nature article indicates that analyses of carbonate deposits within aqueducts reveal evidence of repeated manual removal of calcite, a process requiring ongoing human intervention and therefore a continuous supply of laborers. These maintenance regimes occurred at intervals of 1 to 5 years, suggesting a sustained demand for enslaved or coerced labor even after initial construction was complete. The need for such frequent upkeep further underscores the scale of resources, both human and material, required to sustain Roman aqueduct systems. The Roman Empire's extensive water management networks were central to its growth and stability. Aqueducts, engineered channels delivering water to urban centers, military camps, and industrial sites relied on precise gradients and sometimes inverted siphons to maintain a steady flow over considerable distances. Regular maintenance was as vital as initial construction. Cleaning, inspection, and repair preserved both water quality and flow rates. However, the sustained operation of these systems faced increasing challenges that ultimately contributed to their decline and had significant consequences for Roman cities. The Nature article indicates analyses of carbonate deposits within aqueducts reveal evidence of repeated manual removal of calcite at intervals of 1 to 5 years. This ongoing maintenance requirement demonstrates a continuous demand for labor, even after initial construction was complete. As resources shifted or priorities changed, the ability to sustain this level of upkeep diminished. The decline in maintenance directly impacted water quality and flow rates, leading to reduced access to clean water within urban areas. Studies of pipelines supplying Pompeii's public fountains suggest that flow rates were already carefully managed during Roman times, indicating a sensitivity to efficient distribution. Any disruption to these established systems would have had immediate consequences for the population reliant upon them. The reduction in water flow had cascading effects beyond simple inconvenience. The Nature article notes that analyses of carbonate deposits within aqueducts reveal evidence of repeated manual removal of calcite at intervals of 1 to 5 years, a practice directly linked to maintaining functionality. Consequently, diminished upkeep translated into poorer sanitation and increased risks of disease transmission within urban centers. Public baths reliant on consistent water supply for hygiene and social interaction would have seen reduced operation or closure. Similarly, the fountains that Pompeii's pipelines served, as documented in studies estimating flow rates between 0.1 and 2.5 liters per second, may have become unreliable sources of potable water, forcing residents to seek alternative, potentially less safe supplies. The decline also impacted industries dependent on hydraulic power. The reconstruction of the Barbigol mill complex, utilizing carbonate encrustations, demonstrates how advanced engineering was employed for efficient milling operations. Any disruption would curtail production and economic activity. The disruption to hydraulic power also curtailed activities such as fulling workshops, which relied on water-powered machinery for textile processing. The Nature article highlights that reconstruction of the Barbigol mill complex utilized carbonate encrustations to model a series of 16 overshot wheels. Any decline in consistent water flow would have severely impacted this industrial installation's output and the broader economy it supported. Furthermore, the reduced availability of water likely exacerbated tensions between urban and rural populations, as competition for increasingly scarce resources intensified. The Roman aqueducts, now often romanticized as symbols of a vanished empire, were initially and fundamentally practical infrastructure projects. Their construction represented an extraordinary investment of resources, labor, materials, and engineering expertise, all directed towards securing reliable water supplies for burgeoning urban centers and supporting industrial activity. The Nature article highlights that these structures delivered spring and river water to cities, military camps, and industrial sites, exploiting precise gradients to maintain a steady flow over considerable distances. This wasn't merely about providing drinking water, it was about enabling the scale of Roman society itself. The enduring image of arched aqueducts spanning valleys speaks to their impressive engineering feats. Inverted siphons conveyed water under pressure across depressions, demonstrating an advanced understanding of hydraulics. The very act of constructing these systems, the quarrying and transporting of stone, the precise leveling of gradients, the intricate design of settling basins required a level of organization and technical skill that has contributed to their iconic status. Later analysis of carbonate deposits within aqueducts reveals not just structural information, but also insights into maintenance regimes, demonstrating a commitment to preserving water quality and flow rates. The reconstruction of the Barbegal mill complex in southern France, utilizing these very deposits to model 16 overshot wheels, underscores the integral role aqueducts played in powering Roman industries. The meticulous nature of their construction and maintenance has ensured that Roman aqueducts continue to inspire awe centuries later, serving as tangible reminders of a sophisticated civilization. Analyses of carbonate crusts within these structures have revealed not just structural information but also insights into environmental history and maintenance regimes, demonstrating the Romans' commitment to preserving water quality and flow rates. Research indicates repeated manual removal of calcite at intervals of 1 to 5 years in some aqueducts, reflecting shifting socio-economic conditions and adherence to established practices. Furthermore, stable isotope records from carbonate layers have provided climatic and seismic chronologies extending back to the reign of Nero, illustrating how these deposits function as dual archives, documenting both infrastructure events and environmental changes. The reconstruction of the Barbegal mill complex in southern France, utilizing such encrustations to model 16 overshot wheels, exemplifies advanced hydraulic planning in late Republican and early imperial engineering. Geomatic measurement techniques applied to surviving aqueduct sections south of Rome have enabled more accurate flow reconstructions and assessments of subsidence over time. These enduring structures have transcended their original function as mere conduits for water, evolving into potent symbols of Roman ingenuity and imperial power. The sheer scale of undertakings like the Aqua Claudia, stretching over considerable distances with impressive arcades, serve to project an image of strength and organizational capability across the empire. Geomatic surveys of surviving aqueduct sections south of Rome further illuminate the challenges faced by engineers in maintaining consistent gradients amidst geological shifts and subsidence, underscoring their adaptive problem-solving skills. Recent investigations are revealing new layers of understanding about Roman aqueducts and their operation. Analyses of carbonate crusts, mineral deposits within these channels, have provided insights into past maintenance practices and environmental conditions. For example, studies in southern France show evidence of manual removal of calcite buildup occurring at intervals ranging from 1 to 5 years. This frequency aligns with historical advice regarding seasonal upkeep, suggesting a deliberate effort to maintain water quality and flow rates responsive to changing economic circumstances. Further south, in Turkey, researchers have extracted stable isotope records from carbonate layers within an aqueduct channel. These records offer a chronological timeline extending back to the reign of Nero, demonstrating that these structures inadvertently preserve valuable data about past climates and even seismic activity. The very deposits once considered mere obstructions are now recognized as archives documenting both infrastructure events and broader environmental shifts. Similarly, detailed reconstruction efforts at the Barbegal watermill complex in France utilized carbonate encrustations to model a system of 16 overshot wheels, revealing a bespoke flume design and serial arrangement that represents Europe's first industrial-scale milling installation. Studies of pipelines supplying public fountains in Pompeii have combined elevation surveys with hydraulic modeling to estimate flow rates ranging from 0.1 to 2.5 liters per second, demonstrating the influence of pipe diameter and surface roughness on water distribution under gravity. Research into Roman pressure conduits has detailed designs for inverted siphons constructed from stone, ceramic, and lead, outlining solutions to challenges in sealing, jointing, and air release, techniques that drew upon principles articulated in Vitruvian treatises concerning best practices in pressure line construction. Geomatic measurement techniques have been applied to surviving aqueduct sections south of Rome, using high-precision leveling to reconstruct original gradients and assess centuries of subsidence. These surveys have enabled more accurate flow reconstructions and paved the way for future studies of long-term structural deformation. The Roman Empire's water management networks stand as a testament to an era of remarkable engineering and organization. Central to these systems were aqueducts, structures that delivered spring and river water to urban centers, military camps, and industrial sites across vast distances. Beyond the initial construction, however, lay a continuous cycle of maintenance and repair, performed by laborers whose efforts ensured the consistent flow vital for Roman society. These workers, often overlooked in accounts focused on the grand designs of architects and engineers, were integral to the aqueduct's functionality and longevity. Regular cleaning was as crucial as original construction. Removing calcite deposits at intervals of 1 to 5 years preserved water quality and flow rates. Analyses of incrustations within a southern French aqueduct reveal this repeated manual removal, reflecting shifting socio-economic conditions. The scale of these operations underscores the constant need for skilled labor. Similarly, studies of pipelines in Pompeii highlight the importance of ongoing inspection and repair. Without it, even seemingly minor issues could disrupt water distribution. This maintenance extended beyond simple clearing, encompassing repairs to channels, siphons, and associated infrastructure, a task requiring a diverse skill set among the workforce. The consistent operation of these systems underpinned urban growth, public hygiene, and socio-political cohesion throughout the empire's existence. The consistent operation of these systems underpinned urban growth, public hygiene, and socio-political cohesion throughout the empire's existence. Analyses of incrustations within a southern French aqueduct reveal repeated manual removal of calcite at intervals of 1 to 5 years, demonstrating a sustained commitment to maintaining functionality. Similarly, studies of pipelines in Pompeii highlight the importance of ongoing inspection and repair. Without it, even seemingly minor issues could disrupt water distribution. This maintenance extended beyond simple clearing, encompassing repairs to channels, siphons, and associated infrastructure, a task requiring a diverse skill set among the workforce. The scale and consistency of Roman water infrastructure left a legacy that informs modern water engineering and heritage conservation. Recent investigations into carbonate crusts have provided new insights into both environmental history and maintenance regimes. High-resolution stable isotope records from aqueduct channels in Turkey, for example, have yielded climatic and seismic chronologies dating to the reign of Nero, demonstrating how these deposits serve as archives of infrastructure events alongside paleoclimate data. Furthermore, reconstruction efforts at the Barbagol watermill complex utilized carbonate incrustations to model a series of 16 overshot wheels, revealing advanced hydraulic planning in late Republican and early imperial engineering. These ongoing interventions required not only skilled laborers, but also a degree of organizational capacity to manage resources and coordinate effort across considerable distances, a testament to Roman administrative capabilities.